Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review log scales. So for the first example, I'll use pH. So the pH of a substance in chemistry tells you about how acidic it is. And it turns out it's on a log scale. The number that is the pH, so whether it's pH is 3, 4, whatever, is determined by the concentration of hydrogen ions according to this equation here. So if I have a substance with pH 7, I can find out the concentration of hydrogen ions. So I would have pH, I've substituted for 7, equals minus log 10 of H plus. So I'll just call the concentration of hydrogen ions H there. So I'm going to times each side by -1. So I can get rid of the negative there and put it there. Now the way I get rid of log base 10 is to raise 10 to the power of each side. So I get 10 to the minus 7 equals H. What that means is a substance with pH 7 has a hydrogen ion concentration of 10 to the -7. Now it turns out in water at certain temperature and certain pressure, the concentration of hydrogen ions times the concentration of hydroxide ions is 10 to the -14. So if a substance has this concentration for hydrogen, you can easily figure out it will also have 10 to the -7 concentration of hydroxide. So this means that these two are in perfect balance, the same concentration of both. And so that pH of 7 is the pH of pure water. It's neither acidic nor basic because these two have the same concentration. So by the way, when we say concentration, we're talking about moles per litre. So water has a pH of 7 if it's pure water because its hydrogen ion concentration is 10 to the -7 moles per litre. What about something with pH 6? Well, we could follow the exact same process. We have pH equals negative log base 10 of the hydrogen concentration. We can times each side by -1, raise 10 to the power of each side, and we see that the substance with a pH 6 has hydrogen ion concentration of 10 to the -6. So that means the concentration here would be 10 to the -8 of such a substance in water. So this number is actually 10 times this number here. This has 10 times more hydrogen ions than this here. So if we were to put this on a scale, if a substance has pH 7, then its concentration of hydrogen ions is 10 to the -7. If it's 6, pH is 6, its concentration is 10 to the -6. Predictably, if a substance has pH 5, the hydrogen ion concentration is 10 to the -5. So on a graph, it actually looks like this. Now, it gives the impression of a line, but it's actually not linear because this scale is not going up linearly. It's not going up by the same amount each time. It's being multiplied. So if we start with 10 to the -7, if you times by 10, times by 10, times by 10. So what happens with pH is each time you decrease the pH by 1, you multiply the hydrogen concentration by 10. So if you were to decrease the pH by 2, jump say from 8 to 6, you've multiplied the hydrogen concentration by 10 squared or 100. If you decrease the pH from 8 to 5, if you decrease the pH by 5, you multiply the hydrogen concentration by 10 cubed or 1,000. So each increment of 1 on the pH scale means a 10-fold increase or decrease, depending which way you're going, in the hydrogen ion concentration. Now, the reason that this has a negative slope, the reason that lower pH means more hydrogen concentration is because of this minus at the front. So log scales are like this, they are comparative. Essentially here we're comparing the hydrogen concentration with something like water. Water has a pH of 7 because of this equation here. So if something has a pH of 8, it means it has 10 times fewer hydrogen ions. If it has a pH of 6, it has 10 times more hydrogen ions than pure water. So that's what I mean by comparative. And they're log scales because this scale goes up exponentially. We're timesing by 10 each time. So all scales have that in common, and we'll look at a couple more now. So here we have one formula for earthquake. There's a few different formula, but this one measures the energy in kilowatts. Now, R is so called because of the Richter scale. R is the number that the earthquake registers on the Richter scale. So we're going to investigate how changes in R affect changes in E. So we're going to call two earthquakes. Their magnitudes R1 and R2. So this is R1, so an earthquake with energy 1. This is R2, earthquake with energy 2. So I can simplify this. First thing I can do, I have 1.46 minus 1.46, so they cancel out. Now I have a common factor of 0.67, so I will write that out the front. And then I have log 10 of 0.37E1 minus log 10 of 0.37E2. Now, using the log laws, we are subtracting two logs of the same base, so I can divide these two. When I divide 0.37E1 by 0.37E2, I will cancel out the 0.37s. So I'm going to be left with 0.67 log base 10 of E1 over E2. So if, for example, E1 over E2 was 10, what that means is the energy released by the first earthquake is 10 times larger than that of the second. So if this was 10, I'd have log 10 of 10, which is 1. 0.67 times 1 is 0.67. So what I'm saying here is this scale means that every time you multiply the energy by 10, then the magnitude on the Richter scale goes up by 0.67. So that's how this particular scale works. Now the question asks us if the magnitude increases by 2. So R1 minus R2 I can replace with 2. So let's solve for E1 over E2. So if I divide 2 by 0.67, I get about 2.985. That equals log 10 of E1 over E2. And then to get rid of the log 10, I raise 10 to the power of. So 10 to the power of my previous answer equals E1 over E2. And so the answer I get is about 966. That means if you increase by 2 on the Richter scale, the magnitude goes up by 2, the energy released is about 966 times greater. So this means if you were to go up by 1 on the Richter scale, you would be multiplying the energy by the square root of 966, so about 31 times. So each time you go up by 1 on the Richter scale, the energy released is 31 times greater. All right, let's look at one more example of log scales. So here is the formula for the stellar magnitude. So it's used to indicate the brightness of something in space, like a star, planet, moon, whatever. So here, because of this negative 2.5, it means that objects that are brighter have a lower stellar magnitude. So here B is just the brightness of the object, and B0 is the dimmest object a human can see. So really this is a comparative scale. The stellar magnitude, the number M, is determined completely by how many times brighter an object is than the dimmest item that a human can see. So in this one, we're just asked to rewrite the formula to make B the subject. So we don't even need to know about stellar magnitude and what it does. We're just going to get B by itself. So the first thing we're going to do is divide by negative 2.5. So when you divide by negative 2.5, which is negative 5 over 2, that is the same as timesing by negative 2 on 5. So we get negative 2m on 5 is equal to log base 10 of B over B0. So now we want to get rid of log base 10. We raise 10 to the power of each side. So I get 10 to the power of this is b over b0, and then I simply multiply each side by b0. Now I've got a formula, an equivalent formula where b is the subject, and I'm done. Alright, thank you so much for tuning into this video. Best of luck studying, but you'll ace it, you're a star. This has been the luckiest maths teacher in the world. Have a great day.